Hello folks, welcome back. So this is the last unit associated with the chapter on capacitors. And actually, I'm going to begin by doing a little bit of a retrospective, essentially going back and covering one section from chapter 21, namely section 21.7, and that pertains to electric dipoles. Now, the reason for kind of moving things around a little bit is that electric dipoles are not needed till we get to this point in the course, and therefore it makes sense to kind of teach it to you exactly before it's going to be a needed concept. So with that, let's go ahead and point out a situation where we have two equal and opposite charges, plus q and minus q, and they're separated by, let's say, a distance of 2a. Why 2a? Well, let's just say that that's a convention. So we can go ahead and say that associated with this dipole, we have associated with this configuration of charges, we can actually write down a dipole moment vector. Now, what is the direction of that vector? That direction of the vector is such that it always goes from the negative charge to the positive charge in this fashion. Okay? And what is the magnitude of the vector? The magnitude of that dipole vector, we will say that the magnitude of that dipole vector is just equal to the magnitude of the positive charge times the separation between the two charges, which in our special case is equal to 2a. Now, why do we actually have this concept? We actually have this concept because it is a very useful idea. In other words, many molecules indeed have some or the other approximate shape of a dipole. And in fact, when electric fields are put on molecules of material, they in fact become very much like dipoles. So in a sense, we know that having equal and opposite charges separated by a distance gives us a dipole, but we also now know that many molecules in nature essentially look like and behave like dipoles, which is why this concept has a certain utility, which we're going to exploit in this section. So, the first idea has already been mentioned, which is that you take the charge of the positive charge and multiply it by the separation between the two charges, and that gives you the dipole moment or the magnitude of the dipole moment vector and the direction of the dipole. So we found the magnitude of the dipole moment vector, and then we say that the direction of the dipole moment vector always points from the negative charge to the positive charge along the line joining the negative to the positive charge. Now, the important idea is that dipoles do interesting things when they're placed in electric fields. So what we're going to study in the first place is what happens to a dipole when it is placed in a uniform external electric field. Of course, as we move further in our studies, we will actually go ahead and study what happens to a dipole when it is placed in a non-uniform field. So say if you like that you have a uniform electric field pointed in the x direction, okay, then you can actually say that there's an angle theta made between the dipole moment vector, which is this guy, and the direction of the electric field. That is in fact shown to us in this figure. Now let's go ahead and ask what happens to the dipole when it is making an angle of theta relative to the uniform electric field. That's the simplest thing that we can ask. And we realize that the positive charge experiences a force F, which is just equal to the positive charge itself times E vector. So that positive charge experiences a force which is aligned in the direction of the electric field. However, the negative charge will experience a force that is in the opposite direction, and therefore we say that the force experienced by the negative charge is just given by minus q times E vector. And we realize that these two forces are equal and opposite. So if you imagine that these two dipoles are connected by a rigid stick, which is not a bad approximation for various types of molecules, then we will actually understand that because we have two charges separated by a certain distance, we have a net force on this configuration of two charges that are connected by a stick. We have a net force that is in fact zero. Now notice that this is only in the special case where there's a uniform electric field applied to the two charges. So the dipole experiences a net force in a uniform electric field that is in fact zero. Now, even though the net force is zero, notice that around this fulcrum point, which is the point O shown out here, we have a net torque. So this force on the positive charge applies a torque which is just given by this moment arm times the force. And so if this angle is theta, then the length of this moment arm is just given by A times sine theta. So the positive charge places a torque tau, which is actually, at least whose magnitude is given by Q times E times the moment arm, which is A times sine theta. Notice though that this negative charge also experiences a force that acts along a moment arm, and the length of that moment arm is also equal to A times sine theta. Therefore, we have a further torque from the negative charge, which is also given by plus Q times E times A times sine theta. Therefore, we have a net torque, which is in fact given by 2 Q A times E times sine theta. Now let's go ahead and club some of these terms together so that we can understand them more meaningfully. So if we club 2 times Q times A together, we realize that 2 times Q times A is nothing but the charge of the positive charge of the dipole multiplied by the distance between the two charges, and therefore it is actually equal to the dipole moment, that P itself. So we say that this is just equal to P So this is just equal to P times E times sine theta. Now, realize that P vector is a vector, E vector is the electric field vector, it is also a vector, and therefore P times E times sine theta is very evocative. It basically reminds us that it's basically the magnitude of the dipole moment itself, which is P, times the magnitude of the electric field, which is E, times the sine of the angle between the two objects, and therefore we have a torque which is just given by P times E times sine theta. Now, where have we seen this before? The magnitude of one vector times the magnitude of the other vector times the sine of the angle between them. The answer is that we have seen that with respect to cross products, and so we go ahead and say that the torque, if expressed vectorially, is just given by P vector crossed with E vector, so that we have that sine theta built in automatically. So that is actually the idea. So we understand that a dipole actually experiences a net torque if it's placed inside an electric field, even though it does not experience any net force when it is placed in a uniform electric field. With this insight, we're now ready to go ahead and understand some energy considerations associated with a dipole. So we realize that if we have a dipole, then this dipole is going to experience a torque in this direction. Okay, so it's going to experience a torque in the clockwise direction. And let's say that we have this angle theta, and therefore we're trying to make an angular displacement of d theta in this direction. Then the amount of work that we would do is just given by dW, which is actually minus tau times d theta. So realize that work is equal to force times displacement, but the analog of force for rotational motion is torque, and the analog for displacement is angular displacement, and therefore we have the work done is just equal to minus tau times d theta, and therefore we can write that out explicitly because we have a formula for the torque, which is just P times E times sine theta. So we go ahead and extend this formula out here, and now we realize that the potential energy is actually the negative of the work that we have done, and therefore the infinitesimal change in potential energy of the dipole when it is moved around by an angle theta is given by this formula, and so we go ahead and integrate it out. And so the integral of sine theta is minus cosine theta, and so we obtain the potential energy as being given by minus P times E times cosine theta plus some integrating constant u0. Now we can easily take care of the integrating constant by saying that u0 is equal to 0 when theta is equal to 90 degrees. Okay? So that allows us to actually go ahead and realize that we have P, we have E, and then we have cosine theta. Now that again is very evocative because we realize that when we have two vectors and we have the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them, then that should remind us of the dot product. And therefore, we realize that the potential energy of the dipole is just given by minus of P vector, which is the dipole moment vector, dotted with E vector, which is the electric field vector. Now this is all within the context of a uniform electric field. What we're going to do is actually extend our knowledge by asking what happens if a dipole is placed in a non-uniform electric field. So in a non-uniform electric field, say you have a charge of plus Q out here, that charge produces a non-uniform electric field. So the charge produces an electric field that is stronger out here at the location of the minus charge of the dipole and is weaker at the location of the plus charge of the dipole. Then we realize that because the electric field is stronger at the location of the negative charge in this figure, we have a stronger force acting in this direction on the negative charge, and we have a weaker force acting in the opposite direction on the positive charge. And therefore, we realize that a dipole placed in a non-uniform electric field does not necessarily experience zero force. This notion of the dipole experiencing zero force is only particular to the idea, to the situations when the dipole is placed in a uniform electric field. Now, typically, we're interested in the dipoles that are produced by small molecules, and those molecules typically have a distance of about nanometers, which is 10 raised to minus 9 of a meter, or a tenth of a nanometer, and they have charge separations that are actually measured in terms of E, where E is the unit of charge on the electron, and so we can actually measure dipoles of molecules in terms of electron dotted with nanometers. Now, dipoles are very useful. For example, your microwave would not work if it were not for the fact that the water molecule is itself dipolar. So we'll actually go ahead and see a picture of the water molecule in a couple of transparencies and understand why it is dipolar. But it actually turns out that the water molecule likes to resonate at a certain frequency. In other words, it likes to flip over at a very special frequency, and that frequency corresponds to microwaves that are about approximately 12 inches in length. And so you actually have a situation, 12, I think it's more like 12 centimeters, but let me go ahead and check up on that. Okay, so what happens in a microwave is that you have microwaves being generated with just the right wavelength and the right frequency so as to make the water molecule flip back and forth as it experiences flips in the electric field. And as a result, the water molecule picks up energy from the electric field and therefore becomes even more heated, and that's how microwaves actually go ahead and generate heat. Okay, so just to make clear, my second guess was correct, and microwaves operate with electromagnetic radiation that's about 12 centimeters in wavelength. So with that, let's go ahead and move forward. So now we'll actually go ahead and you can actually see the solved problem, which is a very simple solved problem. So it basically says that the dipole moment is 0.02 electrons times nanometers, which can actually be translated into 0.02 times 1.6 times 10 raised to minus 9 coulombs times 10 raised to minus 9 meters. So this is the charge of an electron multiplied with a nanometer, and that has to be multiplied with the electric field and the sine of the angle between the two electric field and the dipole shown in the figure out here in order to obtain the torque, and likewise we can obtain the potential energy of this situation, of this configuration, and that's nice and simple. The thing that's interesting is this thought question. So I will go ahead and take you all through one part of this thought question, and you guys can go ahead and figure out the other part of the thought question. So we're told that we have an electrically neutral dipole that is placed in an external electric field. Okay? Now, in this situation, we're told that the electric field is actually uniform or not uniform based on the situation. So the upper two panels show the dipole placed in a in a non-uniform electric field. The lower two panels show the dipole placed in a uniform electric field. So the question asked of us is, in which situation is the net force on the dipole exactly equal to 0? Okay, so let's go ahead and find that out. Now, of course, we realize that if we have a uniform electric field, then based on what we've studied so far, we understand that the force on, let's focus on panel C, the force on this positive part of the dipole will be equal and opposite to the force on the negative part of the dipole, and therefore we will have a net force that is exactly equal to 0 in this situation. So in this situation, we have a net force which is exactly equal to 0. What about panel D? In panel D, you have an electric force that is this way on the positive charge. You have an electric force that is this way on the negative charge. And therefore, again, you have a force which is exactly equal to 0. So we see that the net force on the dipole is exactly 0 in the lower two panels. Let's go ahead and examine whether or not the net force is 0 in the upper two panels. In the upper two panels, we see that the positive charge, let's focus on panel A. We see that in panel A, the positive charge is in a location which has a more dilute electric field than the negative charge. So the positive charge will feel a force in the direction of the electric field. However, the negative charge will feel an even stronger force. So we'll draw an even larger vector associated with the force experienced by the negative charge, and therefore we realize that in this situation, in panel A, we have the force being not equal to 0. The same situation happens out here in panel B, where you realize that the positive charge is in a location where the electric field is more dilute, so it feels a smaller force. The negative charge is in a location where the electric field is less dilute, namely stronger, and therefore it feels a larger force. And therefore, in panel B also, we have force not being equal to 0. So with this understanding, we realize that in panel C and D, we have no net force, and that's the question asked of us in thought question number 6, which is that in which situation is the net force on the electric dipole 0? And the answer is that uh, in C and D, which is answer number 5, the net force is indeed 0. Thought question number 6 provides a variant on that, basically asking about the situations where the net torque is 0, and you have enough information in front of you for you to be able to think about the net torque in the various situations. So please go ahead and think about it and come to class with the right answer. So with this, let's move on. So we have essentially uh, polar and nonpolar molecules. We'll essentially understand that with examples. So imagine, if you like, that we have a water molecule. Now the angle made by the hydrogen atoms relative to the oxygen atom is such that it's not a simple straight line. Okay, the typical water molecule will have hydrogen bonds making an angle of 105 degrees, and the nature of oxygen atom is such that it actually likes to acquire negative charge. The nature of the hydrogen atom is such that it actually likes to donate away its the charge of the electron that is bound to it, and as a result you have a substantial concentration of negative charge at the location of the oxygen atom. And if you take the average of the location of the hydrogen atoms, you actually realize that their center of gravity or center of mass is out here, and so you have a net concentration of positive charge at this location. And so you can actually go ahead and say that there is a dipole moment p vector associated with the water molecule, and therefore you realize that a water molecule placed in an electric field will actually want to align itself in the direction of the electric field so that its dipole is aligned in the direction of the electric field. Now, what happens if the electric field keeps flipping? So if you have the electric field down like this for one instant, another instant it becomes up like this, and another instant it becomes down like this, and another instant it becomes up like this, the answer is that the water molecule will keep flipping up and down, up and down, up and down, and as a result, it will acquire a lot of energy, or it will acquire a lot of kinetic energy or oscillation energy, and that's exactly what happens in a microwave. So in a microwave, there's an oscillatory electric field, and the wavelength of that electric field is about 12 centimeters, and that electric field therefore ensures that the water molecules in your food, most foods have a lot of water molecules, and it therefore ensures that the water molecules inside your food keeps acquiring energy by flipping back and forth, and that actually goes ahead and heats up the food. So we actually understand how polar molecules work. Namely, polar molecules are molecules that have an intrinsic dipole moment, but even if you don't have a polar molecule, even if you have a molecule that initially does not have any net dipole moment, you can see that here you have a linear molecule. The center is at the center and the two ends are positively charged. Even then, if you apply a net external electric field like so, then you will have a situation where the negative charge will experience a force and want to displace itself in this direction, and that will create a situation where you have a net electric dipole moment like so. So you actually have a net induced electric dipole moment, or what we call an induced polarization, that will want to line up in the direction of the electric field. Okay, so many objects, even if they're initially unpolarized, will actually acquire a polarization if they're put inside a strong electric field. And now this actually begins to explain to us what happens when you have dielectrics that are placed inside a capacitor. Because when placed inside a charged capacitor, the dielectric essentially begins to feel a net external electric field, and therefore the molecules that make up that dielectric, and remember that dielectrics are basically non-conductors, the molecules that make up a dielectric will basically want to go ahead and develop a polarization in the direction of the externally applied electric field. We've seen that out here, and we've also seen that with the water molecules in the previous transparency. So now let's go ahead and understand at a molecular level how you have um, or how a dielectric material responds when it is put between the plates of a capacitor. Now, this picture out here shows you a typical dielectric material, and the positive and negative charges, the red and blue ovals, basically are meant to represent molecules in this material, magnified, of course, millions of folds or billions of folds. And we see that when nothing special is done to the molecules, they're on average randomly oriented. So if you draw any circle at any location, you realize that the net charge that you're approximately going to have within that circle will be exactly zero because of the random orientation of the molecules. Now let's go ahead and ask what happens if this dielectric is placed between this positive and negative charge plates out here. If placed between the plates, then you have a situation where if you draw a circle out here, you will indeed still see that the net charge is indeed equal to zero inside the circle. However, you will actually see something else happening, which is that if you draw a rubber band out here, you will see that the molecules have lined themselves up in the direction of the electric field so that you have a layer of positive charge at the right boundary of this dielectric. And if you draw a similar rubber band out here, you will actually experience a layer of negative charge at the left boundary of this dielectric. So what we see is that when placed inside an external electric field, these dipole-like molecules that make up a dielectric will actually go ahead and align themselves in the direction of the electric field. So the molecules in a dielectric align themselves with the direction of the electric field, exactly as shown in the figure. Now, the extent of the alignment depends on a multitude of factors. For example, if the temperature is very large, then the molecules will want to jiggle more, and therefore their ability to align will actually be diminished. On the other hand, if the external electric field is made stronger, then the alignment will indeed increase with the strength of the external electric field. And so we have the net effect that you have a situation where a net positive surface layer of charge is built up at the right boundary of this dielectric. Notice that the right boundary of the dielectric is the one that faces up to the negative plate of this charge capacitor, and a layer of negative charge is built up at the face of the dielectric that faces up to the positive charge out here. So we call these charges that are produced inside the dielectric induced surface charges, and we have a situation where you have induced surface charge densities at the boundaries of the dielectric. Notice that these surface charge densities are nevertheless produced in molecules that are non-conductors. And if they're non-conductors, the positive charge that is produced in this layer out here cannot go and short itself with the negative charge that is there on this conducting plate. Likewise, the negative charges that you see out here cannot go and short themselves with the positive charges that are present in the conducting plate. Why? Because the positive and negative charges inside the dielectric are basically bound to their parent atoms. They're not free charges that can move around in the entire dielectric, as is the case for metals. So we see a situation that can be modeled by the lower panel, where you have a plus surface charge density on the external metallic positive plate, and you have a minus sigma amounts of surface charge density on the external metallic negative plate. And now imagine that the yellow slab of dielectric has been placed between the two plates. In that case, we have an induced charge that is positive at the right boundary of this dielectric, and we have an induced charge that is negative on the left boundary of this dielectric. So what we see happening because of the presence of the dielectric is that to some extent, if you imagine that we had an original electric field that was strong in this direction, okay, now imagine that the dielectric slab has not been put in, then the presence of the dielectric essentially gives us a layer of positive charges on the right boundary of the dielectric and a layer of negative charges at the left boundary of the dielectric. Notice that the induced charges are never so strong as to exactly be equal and opposite to the original free charges on the conductors. However, the induced charges can actually be a certain fraction of the free charges that we have on the conductors, and as a result, the yellow situation, the yellow dielectric produces, notice that we have a positive charge on the right boundary of the dielectric and a negative charge on the left boundary of the dielectric. So if I draw just the electric field produced by the dielectric, it will be a smaller electric field in the opposite direction. Okay, so if I ask then what is the net electric field that I will have, that net electric field I can draw with a green color, which will actually be about this much. Do you see that? So some of the positive red electric field that was originally present is counteracted by the presence of the induced charges on the dielectric that we have out here. So just to recap, originally imagine that dielectric is not present, namely the yellow slab is not present, and then we actually have the red electric field between the positive and negative plates of the original unfilled capacitor. We then put in the dielectric, and what we do in the process of putting in the dielectric is that we induce a positive surface charge density on the right boundary of the dielectric. We induce a negative surface charge density on the left boundary of the dielectric, and therefore notice that these induced surface charge densities are oppositely oriented to the original surface charge densities on the conductors themselves, and therefore we go ahead and we drew the electric field associated with these induced charges as the little blue vectors that are oriented so that they're going from right to left. Okay? Therefore, we can go ahead and draw the net electric field, which is the red electric field minus the blue electric field, which is in fact the green electric field that I'm making even more solid right now. But what is the upshot? The upshot is that the green electric field that is produced in this configuration with the dielectric present between the conductors is indeed smaller than the original red electric field that was present before we stuck the dielectric slab between the plates of the conductor. And that is the important insight that I want you all to have, namely that the net electric field obtained after so if you imagine that E0 is the original electric field before any dielectric has been put in, and if you imagine that the net electric field after the dielectric has been put in is E, then E is equal to E0 divided by the dielectric constant kappa. Since kappa is larger than unity, the electric field that is present in the final configuration after the dielectric slab has been snuck in is indeed smaller than the original electric field. So we can actually say that E is less than E0 because kappa is greater than 1. Okay? So now we're going to go ahead and realize that the electric field in the dielectric is diminished because of the induced surface charge densities that are initially produced when the dielectric is snuck in. And these surface charge densities indeed counteract the surface charge densities on the metallic plates, thereby diminishing their effect. So these are the insights that we carry through, and now go ahead and carry these insights into this last transparency associated with this chapter. So we say that we're starting with some free charges, sigma f and minus sigma f, on the positive and negative plates of this capacitor. Imagine for now that the dielectric has not been snuck in, and therefore we have an electric field E0 which is pointed to the right and is shown by this big red arrow. So the big red arrow shows the original electric field before the dielectric is present. And this big red arrow is just sigma f, the surface charge density of the free charges on the plates, or at least the surface charge density on the positive charge of the plate, and this other plate has a negative surface charge density, equal and opposite. So the electric field in the original configuration before the dielectric is inserted is just given by sigma f divided by epsilon naught. Now, because of the presence of the dielectric, we have a situation where we produce a layer of induced surface charge densities, and these induced surface charge densities are oppositely oriented, namely the induced surface charge density on the right part of the dielectric. So now we've inserted the dielectric between the plates and we have an induced surface charge density, and on the right side of the dielectric we have an induced positive surface charge density. On the left side of the dielectric we have an induced negative surface charge density, and therefore these surface charge densities, now realize that these induced surface charge densities are always somewhat smaller or significantly smaller than the original charge densities that we have on the conductors. So we can actually go ahead and say that because of this induced surface charge density, just the contribution from the induced surface charge density is shown by the blue vector, and this blue vector, because the induced surface charge densities are oppositely oriented, produces an electric field that is given by the induced electric field, which is just minus sigma induced, which is the surface charge density of the induced charge divided by epsilon naught. Now, what is the net electric field? The net electric field is shown by the black arrow, which is actually the red arrow minus the blue arrow. And you see that the net electric field in the final configuration is indeed smaller than the original red electric field. So that is given by taking E0 and subtracting off the induced electric field, and that's exactly what we do. So we vectorially add the induced electric field to the original electric field. So if we add this guy to this guy out here, the result is this guy. So we see that this guy is just the free surface charge density minus the induced surface charge density divided by epsilon naught. You can go ahead and add up this guy with this guy to see in fact that this is so. So this is the net resulting electric field, namely the black vector that is shown out here. So we can actually go ahead and mark up the figure, and so we can say that E0 is in fact the red vector that is shown out here, and E is the black vector that is shown out here. And what is the relationship between E and E0? The answer is that E is equal to E0 divided by kappa. Kappa is greater than unity, so the net electric field after dielectric insertion is smaller than the original electric field before the dielectric was inserted. The original electric field is E0, the final electric field after dielectric insertion is E, and kappa is greater than unity. Therefore, I can go ahead and take the formula for E that I have developed out here, and I can say that that is just equal to sigma f minus sigma induced divided by epsilon naught, and that should be equal to E0 divided by kappa. But I have my formula for E0 being given by sigma f divided by epsilon naught. So I have sigma f divided by kappa times epsilon naught. Now this allows us to go ahead and obtain sigma induced in terms of sigma f. So I can actually go ahead and take sigma induced on the left hand side, and I obtain and take all the terms associated with sigma f to the right hand side. That is an easy calculation to do. And the net result is that I obtained this important result out here, which tells me that the induced surface charge density is equal to the original surface charge density multiplied by 1 minus 1 over kappa. So kappa is greater than 1, so 1 over kappa is less than 1, and therefore 1 minus 1 over kappa will in fact be some factor that is less than unity in general. So let's go ahead and understand how this works. So if kappa is equal to 1, which applies to a vacuum, then we have a situation where the induced surface charge density is exactly 0. So it tells you that in a vacuum or in air, which behaves pretty much very close to a vacuum because it's such a rarefied object, therefore in air or in vacuum, we have kappa equal or nearly equal to 1, or in air kappa is nearly equal to 1 but slightly larger than 1. In a vacuum, kappa is exactly equal to 1, and so in such situations the induced surface charge density is very tiny or 0 and therefore negligible, and therefore we can say that the induced surface charge density is 0. When you have a when you have a conductor though, so assume if you like that this dielectric slab were in fact not a dielectric slab but a conductor, then for conductors, kappa is actually equal to infinity. Therefore, 1 over kappa is actually equal to 0, and therefore that tells you that the induced surface charge density sigma induced is actually equal to sigma f. So in the case of a conductor, the induced surface charges are exactly equal and opposite to the surface charges on the on the two plates that make up the capacitor, which is why indeed if you were to put a conducting slug between the two plates of the capacitor, as we've done in many problems before, you would have a net electric field inside that slug which is exactly equal to 0. So with this, we have understood all the different limiting considerations, and now we have a net, comprehensive understanding, even at the microscopic level, of how you have dielectrics and how they produce a reduction in the electric field inside a capacitor. So with that, I will essentially thank you all for your attention. Hope you've learned a lot. Hope you've developed a lot of insights associated with capacitors, and in the next few chapters, we'll carry these insights forward. So thanks a lot and see you all later. Thank you.